Welcome to the deep dive. Today, we're going to be taking a deep dive into the world of reconfigurable intelligent surfaces, or they're also called RIS. And you've sent over some fascinating research on a new method for optimizing these systems, which really could have huge implications for the future of wireless communication.
Absolutely. RIS is becoming increasingly important as we kind of move towards, 6G and beyond, but optimizing them can be very computationally intensive. So this new research proposes a far-field approximation that could significantly cut down the simulation time while still, maintaining accuracy.
Okay, so let's unpack this. I know RIS act like smart mirrors, kind of redirecting signals to improve coverage and speed. But just remind me why optimizing these setups is so complex.
Sure. So each RIS surface is made up of many individual elements, and each element can be tuned to adjust how it interacts with the incoming signal. So finding the best configuration for all those elements, considering things like the position of the transmitter and receiver, the surrounding environment, and the desired signal characteristics. It's a massive computational challenge.
So traditionally, how have researchers tackled this optimization problem?
So the standard approach has been to run full-wave simulations, which essentially try to model the complete behavior of the electromagnetic waves as they interact with the RIS and the surrounding environment. But as you can imagine, these simulations are incredibly detailed and time-consuming, especially for large and complex RIS setups.
That makes sense. So this new research is proposing a shortcut, a way to simplify the calculations without sacrificing too much accuracy.
Exactly. They call it a far-field approximation method. And instead of simulating every possible scenario, this method uses a single multi-port simulation to create a template that can be adapted to different positions and angles of the transmitter and receiver.
Okay, so it's like creating a master key. That kind of unlocks a range of possibilities without having to craft a new key each time.
Yeah, that's a great analogy. Now, to really understand how this works, we need to kind of dive into the math a bit. The paper lays out two key equations that are really central to this method.
Okay, I'm ready to kind of get into the nitty-gritty. Where do we start?
Let's start with equation 1. It focuses on estimating the coupling between the transmitter, each element on the RIS, and the receiver. So this coupling essentially represents the strength of the signal transfer between these components.
So it's telling us how much of the signal is actually going to make it from point A to point B, considering all the factors that can influence signal strength along the way.
Precisely. And the equation takes into account a few key factors. First, there's the distance between the transmitter, the RIS element, and the receiver. The farther apart they are, the weaker the signal will be.
Right, that's pretty intuitive. The signal strength decreases with distance. What else is factored in?
The angle at which the signal hits the RIS is also crucial. Think of how a satellite dish needs to be pointed directly at the satellite to receive the strongest signal. Similarly, the orientation of the RIS element relative to the transmitter and receiver significantly affects the coupling.
So it's not just about distance, it's also about alignment. What about the properties of the elements themselves? Do those play a role in the coupling?
Absolutely. The equation 1 also considers the gain of each element. Gain essentially represents how well each element can transmit and receive the signal. You can think of it as a measure of the element's efficiency in capturing and redirecting the signal.
So a higher gain means a stronger signal transfer. It sounds like this equation is elegantly capturing all the key factors that influence signal propagation in this scenario.
It is, and it does so in a way that significantly simplifies the calculations compared to the traditional full-wave simulations.
Okay, so we've got equation 1, which gives us the coupling for a single element on the RIS. But how does this relate to the overall behavior of the entire RIS system, which might have hundreds or even thousands of elements?
That's where equation 2 comes in. It essentially creates a blueprint for the entire system by organizing all those individual coupling estimations into a matrix.
A matrix. So it's like a grid of numbers where each cell represents the coupling between two specific points in the system.
Exactly. Each row and column in the matrix corresponds to a particular element in the system, the transmitter, the receiver, and all the individual elements on the RIS. So if you want to know the coupling between the transmitter and the third element on the RIS, you would look at the cell located at the intersection of the transmitter's row and the third element's column.
I'm starting to see how this matrix provides a comprehensive overview of the entire system's behavior. It's like having a map that shows all the possible signal paths and their strengths.
That's a great way to put it. And what's remarkable is that this matrix, derived from these simplified far-field approximations, captures the essence of the system's behavior without having to resort to the computationally intensive full-wave
It
simulations.
sounds almost too good to be true. Did they actually build something to test this out in the real world?
They did. The researchers designed and built a small RIS prototype to validate their method.
All right, let's dive into the details of this prototype. What did it look like? And how do they actually test it?
Okay, so the RIS prototype they constructed for this experiment was a rectangular surface, roughly 30 centimeters long and 10 centimeters wide. This surface housed a grid of 14 individual elements, arranged in a 7 by 2 configuration.
So not a massive surface, but enough elements to showcase the functionality and test the accuracy of their approach. What about the individual elements themselves? What were those made of?
Each element was carefully crafted, incorporating something called varactor diodes. These diodes are crucial because their capacitance, their ability to store an electrical charge, can be controlled electronically.
So by adjusting the voltage applied to each diode, they could fine-tune the capacitance of each element, essentially controlling how it interacted with the incoming signal.
Exactly. This level of control is key to being able to test and validate the theoretical predictions of the far-field approximation method.
So they've got this RIS prototype, each element meticulously crafted and tunable. What about the transmitter and receiver? How did they set those up?
For both the simulations and the physical measurements, they used horn antennas for both the transmitter and receiver. These horn antennas are known for their directionality, meaning they emit and receive signals in a focused beam, which is important for this type of experiment.
I see. So they could carefully control the angles at which the signals were transmitted and received, allowing them to test the RIS prototype under different scenarios. Where were these antennas positioned relative to the RIS?
The horn antennas were placed a couple of meters away from the RIS surface. This distance is significant because it places the experiment firmly in the far-field regime, which is a key assumption underlying the far-field approximation method they were testing.
That makes sense. They wanted to ensure that the experimental conditions aligned with the assumptions of their model. So with the RIS prototype, the horn antennas, and the ability to precisely control angles and distances, they had all the pieces in place to put their far-field approximation method to the test.
They did, and the results they obtained were incredibly promising. But before we kind of dive into those, I think it's worth taking a closer look at the specific details of equation 1 and how it captures the essence of signal propagation in this far-field scenario.
I'm all for that. We've talked about it in general terms, but I'm curious to understand the equation itself.
All right, so if we look at equation 1, you'll notice it consists of several factors multiplied together. Each of these factors represents a key aspect of how the signal travels from the transmitter to the receiver via the RIS.
Okay, I'm ready to break it down. What's the first piece of this equation puzzle?
The first term is a square root, specifically the square root of 1 minus the absolute value of spam squared. This part might seem a bit cryptic at first glance, but it's actually addressing a crucial factor known as impedance mismatch.
Impedance mismatch. That sounds familiar, but remind me what that is exactly.
Think of it like this. You're trying to connect two hoses with different diameters. You're going to lose some water pressure when the water flows from the larger hose to the smaller one, right?
Right. Some of the water pressure is lost because the smaller hose restricts the flow. So how does this relate to signal transfer?
In a similar way, when an electromagnetic wave travels from one component to another, like from the transmitter to the RIS, some of the signal can be lost if the impedance of those components doesn't match up perfectly.
I see. So impedance is like a measure of how well a component can accept and transmit a signal without any loss. And a mismatch in impedance means there's going to be some signal loss at that interface.
That's exactly it. And this first term in equation 1 is accounting for that potential loss due to impedance mismatch on the RIS side. They assume the transmitter and receiver antennas are perfectly matched. So we're really focusing on how well the RIS is accepting the signal from the transmitter and then retransmitting it to the receiver.
So the smaller the impedance mismatch, the closer this whole term gets to 1, meaning less signal loss. What's next in this equation?
The next part is all about the antenna gains. We have the square root of GTX times GM, DTX down Sam. Remember, GTX represents the gain of the transmitter antenna, and GM DTX represents the gain of the moth element on the RIS in the direction of the transmitter.
Okay, so we're essentially multiplying the transmitting power of the transmitter antenna by the receiving power of the specific RIS element we're looking at. The stronger each of these is, the stronger the overall coupling.
Exactly. And you'll notice that the gain of the RIS element, GM, is actually a function of the angle GOT XM. This means that the effectiveness of the RIS element in receiving the signal from the transmitter depends on the angle at which the signal hits it.
This makes perfect sense. Just like how a satellite dish needs to be pointed in the right direction to pick up a signal, the orientation of the RIS element relative to the transmitter matters.
You got it. Now, the next part of the equation might look familiar from physics class. It's the term 4dTxml. This is essentially dealing with how the signal strength decreases as it travels over a distance.
Ah yes, the inverse square law. The farther the signal has to travel, the weaker it gets. In this case, dTxm represents the distance between the transmitter and the specific RIS element. And AOI law is the wavelength of the signal.
You're absolutely right. And finally, we have the term EG2TXml. This part might seem a bit more abstract, but it's accounting for the phase shift of the signal.
Phase shift. Remind me what that is again?
Imagine two waves traveling together, if they're perfectly in sync. With their peaks and troughs aligning, they're said to be in phase. However, if one wave is slightly ahead of the other, their peaks and troughs no longer align perfectly. This offset is called the phase difference or phase shift.
Okay, so the phase shift basically tells us how much one wave is shifted relative to another. What does that have to do with the signal traveling from the transmitter to the RIS?
As the signal travels that distance, dTxm, its phase changes. This term in the equation is capturing that change in phase. And the reason this is important is that when the signal arrives at the RIS element, it might be slightly out of phase with signals arriving from other elements.
Right. And depending on how these signals align, whether they are in phase or out of phase, they can either reinforce each other or cancel each other out, which can significantly impact the overall signal strength.
You've got it. So in a nutshell, this entire equation 1, despite its seemingly complex form, is elegantly capturing the essence of how a signal travels from the transmitter to an individual RIS element, taking into account factors like impedance mismatch, antenna gains, signal attenuation over distance, and the crucial phase shift that occurs during propagation.
That was an incredibly insightful breakdown. I feel like I have a much deeper appreciation for the complexity involved in accurately modeling how these signals behave. And what's amazing is that this equation manages to condense all of that complexity into a relatively compact form.
And remember, this is just for a single element on the RIS. When we bring in equation 2, we're essentially applying the same logic to every single element, creating a comprehensive model of the entire system.
Right? Equation 2 takes all those individual coupling values, calculated using equation 1, and organizes them into a matrix that represents the entire system. This matrix gives us a powerful tool to analyze and optimize the RIS as a whole.
Exactly. And it's this matrix that forms the foundation for their far-field approximation method, allowing them to predict the behavior of the RIS under different scenarios without the need for time-consuming full-wave simulations.
I'm really starting to see the potential of this approach. By simplifying the calculations without sacrificing too much accuracy, it could significantly accelerate the design and optimization of these RIS systems.
It could indeed. And the experimental results they obtained with their prototype provide compelling evidence to support this claim. But I think we'll save that discussion for part 2 of our deep dive.
Sounds good to me. We've covered a lot of ground already, delving into the intricacies of equation 1 and how it captures the physics of signal propagation in this far-field scenario. I'm eager to hear about the results of their experiments and what those results mean for the future of this technology.
I'm equally excited to share those findings with you. We'll uncover how their far-field approximation method performed in the real world, and we'll explore the broader implications of this research for the future of wireless communication.
Until then, keep those minds curious and those connections strong. We'll be back soon with part 2 of our deep dive into the world of reconfigurable intelligent surfaces.
Welcome back to our deep dive into the world of reconfigurable intelligent surfaces. In part 1, we unpacked the core concepts behind a new method for optimizing these systems, and we even started to break down the math with equation 1, which estimates the signal coupling between the transmitter, an individual element on the RIS, and the receiver.
We also touched on equation 2, which essentially takes all those individual coupling values and organizes them into a matrix that represents the entire RIS system.
Right, and this matrix is key to the far-field approximation method because it allows us to predict how the entire system will behave under different conditions without resorting to those computationally intensive full-wave simulations.
So it's all about simplifying the calculations without sacrificing accuracy. And speaking of accuracy, I'm dying to hear how this method actually performed when they put it to the test with their real-world prototype.
This is where it gets really exciting. The researchers meticulously designed and built this prototype specifically to validate their approach. They carefully chose a small rectangular surface with 14 elements arranged in a 7x2 grid. Each element incorporated varictor diodes, which allowed them to electronically control the capacitance of each element.
So they could precisely tune each element on the RIS to match the values predicted by their optimization method.
Exactly. And they went to great lengths to create a controlled testing environment. They used horn antennas for both the transmitter and receiver, placing them a couple of meters away from the RIS surface to ensure they were operating in the far-field regime.
So it was all about carefully controlling the variables, distances, angles, and the properties of each element to ensure the experimental conditions matched the assumptions of their model.
Precisely. They wanted to eliminate any potential sources of error that could skew the results and obscure the true effectiveness of their far-field approximation method.
It sounds like they were incredibly thorough in their approach.
All
All right, let's get to the good stuff. What did the results actually show?
The results were remarkably consistent across the board, providing strong evidence to support the validity and accuracy of their approach first and foremost. The capacitance values they derived using their simplified far-field approximation method were nearly identical to the values obtained from the much more time-consuming full-wave simulations.
Wow, that's huge validation right there. It means that their simplified approach can deliver accurate results without sacrificing precision, which is a massive win in terms of efficiency.
Absolutely. And this consistency wasn't just limited to numerical comparisons. They took those capacitance values derived from their method and physically implemented them on their prototype using those varictor diodes. They carefully adjusted the voltage applied to each diode to fine-tune the capacitance of each element, essentially bringing their theoretical predictions to life in the real world.
It's like they were conducting a symphony of signals, precisely controlling each element on the RIS to create the desired outcome.
I love that analogy. And the results of this meticulous orchestration were equally impressive when they measured the actual performance of their optimized RIS prototype. They found that the results closely matched both the values predicted by their far-field approximation method and the results of the full-wave simulations.
So across the board, theory, simulations, and real-world measurements, their method consistently delivered accurate and reliable results. That's a trifecta of validation.
It is. And to put the performance of their RIS prototype into perspective, they also compared it to a standard copper reflector. This is a common benchmark in this type of research because a copper reflector simply bounces the signal back without any intelligent manipulation.
Right, it's like a dumb mirror compared to the smart adaptable surface of the RIS.
So how did the RIS prototype stack up against this basic reflector?
Even though the RIS prototype was relatively small, it significantly outperformed the copper reflector, especially when the receiver angle was aligned with the direction the RIS was optimized for.
So their optimized RIS, even in its small-scale form, was able to concentrate the signal power much more effectively than a passive reflector, resulting in a significantly stronger received signal.
Exactly, and they observed this superior performance across a range of receiver angles, demonstrating the adaptability and effectiveness of their optimized RIS design.
This is truly exciting stuff. It seems like this far-field approximation method has the potential to revolutionize the way we design and optimize these RIS systems. It does. By dramatically reducing the computational burden, it opens up a whole new world of possibilities for exploring more complex and efficient RIS configurations, ultimately leading to faster, more reliable, and more secure wireless communication networks.
This deep dive has been incredibly insightful. We've gone from the conceptual underpinnings of RIS to the nitty-gritty details of Equation 1 and its role in this new optimization method, and now we've seen how it all comes together with real-world testing and impressive results.
It's been a fantastic journey so far, but there's still so much more to explore in your roll time. Part 3 will dive deeper into the implications of this research and discuss what it means for the future of wireless communication as we move towards 6G and beyond.
I can't wait. We've talked about the technical achievements, but I'm also curious about the broader impact. How will this technology shape the way we connect and communicate in the years to come?
We'll uncover all that and more in the final part of our deep dive. We'll explore how RIS could revolutionize everything from mobile networks to smart homes and even contribute to a more sustainable and connected future.
Until then, keep those minds curious and those connections strong. We'll be back soon with the thrilling conclusion of our deep dive into the world of reconfigurable intelligent surfaces. Welcome back to the deep dive. In parts 1 and 2, we really dug into the technical details of this new method for optimizing reconfigurable intelligent surfaces. It's amazing how they've managed to simplify those complex calculations with their far-field approximation, and the results they're seeing are truly remarkable.
It's a real game changer. Not only does this approach significantly reduce the computational burden, but it also opens up a world of possibilities for exploring more complex and efficient RIS configurations.
Exactly. We talked about the theory, delved into the math behind those key equations, and saw how their prototype actually outperformed a traditional copper reflector in real-world testing. But now I want to shift our focus to the bigger picture. What does this breakthrough mean for the future of wireless communication?
That's the most exciting part. This research isn't just an academic exercise. It has the potential to transform the way we connect and communicate in the years to come.
I'm ready to hear about these potential applications. Where do you see this technology having the biggest impact?
One area where RIS is poised to make a huge difference is in mobile networks, especially as we move towards 6G and beyond. Imagine a city covered in a network of interconnected RIS surfaces strategically placed on buildings, lampposts, even billboards. These surfaces could work together to intelligently guide and shape wireless signals, creating a much more efficient and robust network.
So instead of relying solely on powerful cell towers to blast signals over long distances, we could have a more distributed and intelligent infrastructure with RIS surfaces acting like smart relays, guiding signals around obstacles and directly to users.
Precisely. This could lead to significant improvements in coverage speed and reliability, particularly in dense urban environments where signals often get blocked or interfered with.
Sounds like RIS could finally solve the age-old problem of dropped calls and dead zones in our cities.
It very well could. And the benefits go beyond just better connectivity by intelligently managing signals. RIS could also contribute to making wireless networks more energy efficient.
That's an important consideration. As our reliance on wireless technology continues to grow, how would RIS contribute to energy savings?
Well, with traditional networks, cell towers often need to transmit at high power to ensure signals reach users in challenging environments. But with RIS, we can strategically redirect and focus those signals, reducing the need for such high transmission power.
So it's like using a flashlight with a reflector. The reflector concentrates the light beam, allowing it to travel farther with less energy.
That's a great analogy. By reducing the energy consumption of cell towers and other wireless infrastructure, RIS could contribute to a more sustainable and eco-friendly communication system.
That's fantastic. It's not often that a technological advancement promises both enhanced performance and reduced environmental impact.
It's a win-win situation, and the potential applications go far beyond just mobile networks. Think about the growing number of smart devices in our homes and workplaces. Everything from smart appliances and security systems to wearables and sensors, they all rely on wireless connectivity to function.
That's right. The Internet of Things is exploding, and we need a robust and efficient infrastructure to support all those connected devices.
And that's where RIS can play a key role by embedding RIS surfaces into the walls, ceilings, even furniture of our homes and offices. We could create a truly seamless and optimized wireless environment.
No more struggling to find that sweet spot for your Wi-Fi router. We could have strong, reliable signals throughout the entire space, eliminating those frustrating dead zones we all know and hate.
Exactly. And it's not just about eliminating dead zones. RIS could also help manage the growing complexity of these indoor wireless networks, ensuring that all those smart devices can communicate reliably and securely without interfering with each other.
This is starting to paint a picture of a future where wireless connectivity is as ubiquitous and reliable as electricity seamlessly integrated into every aspect of our lives.
It's a compelling vision, isn't it? And one that's becoming increasingly achievable thanks to advancements in RIS technology and optimization methods like the one we've been discussing.
This has been an incredible journey exploring not only the technical intricacies of this research, but also its far-reaching implications for the future of wireless communication. I'm truly excited to see how this technology evolves and transforms the way we connect and interact with the world around us.
I share your enthusiasm. This is just the beginning of the RIS revolution, and the possibilities are truly boundless.
Thank you for joining us on this deep dive into the world of reconfigurable intelligent surfaces. We hope you've enjoyed exploring this cutting-edge research with us, and we encourage you to continue your own journey of discovery into the fascinating world of wireless innovation.
Until next time, keep those minds curious and those connections strong.
Welcome back, everybody. Ready for another deep dive?
Absolutely. Always excited to explore new research.
Well, today we're diving into the world of Reconfigurable Intelligent Surfaces, or RIS for short.
Ah, yes, RIS. Intelligent antenna arrays that can manipulate wireless signals. Fascinating stuff.
Yeah, they're really poised to be a game changer for 6G and beyond.
I've been hearing more and more about them lately.
Imagine a world where your phone, it never loses signal.
Because the environment itself is redirecting it.
Exactly. The environment helps to redirect the signal back to you. Pretty cool, huh?
That's the promise of RIS for sure.
And for this deep dive, we're looking at some really cutting-edge research from OST, Eastern Switzerland University of Applied Sciences.
Oh, I'm familiar with their work.
They teamed up with University College Dublin on this one.
It's strong collaboration.
And they're proposing a new method for optimizing RIS using an efficient far-field approximation.
Interesting. So potentially making simulations much faster.
Much, much faster.
Yeah.
And more efficient, too.
Efficiency is always key, especially when we're talking about complex simulations.
You know, it's a big deal in this field. The computational demands can be pretty intense.
I can imagine. Optimizing these surfaces with all their individual elements, it gets complicated quickly.
Yeah, and what I find particularly cool is that they didn't just stop at simulations.
Oh, so they actually built something.
They did. They put their method to the test with real-world measurements using a small 7x2 element RIS.
So we're talking about tangible results here, not just theoretical concepts.
Right. We're going to be looking at real measurable data.
Yeah.
So let's get down to the nitty-gritty. What's the big challenge with RIS?
Well, at the core of it, it's figuring out those optimal reactance values.
Reactance values, okay.
For each individual antenna element on the surface.
Each one. There's a lot of them.
Right, and you have to tune them just right to maximize the power transfer between the transmitter and receiver.
I'm picturing like adjusting a bunch of tiny mirrors to bounce light to a very specific spot.
That's a great analogy. It really captures that level of precision involved in manipulating those electromagnetic waves. The traditional methods, they do work,
Right.
but they are computationally expensive. Imagine having to run a whole new simulation every time you slightly change the position of the transmitter or receiver.
Oof, I can see how that would eat up a lot of time.
It's a very time-consuming process, even with powerful tools like the multi-level fast multi-pole method.
Okay, so that's where this far-field approximation comes in, right?
Exactly. This new method, it's like almost like finding a shortcut.
I like shortcuts.
In a way, they're cheating the system, but in a brilliant way.
And good cheat.
They realized you can actually extrapolate those scatter matrices.
Scatter matrices.
Yeah, they describe how the RIS interacts with the signal, and they realized you can extrapolate them for any transmitter and receiver position from just one single initial simulation.
Wow, so you're saving a ton of time.
A huge time saver,
Yeah.
and it makes that entire optimization process way more efficient.
That's amazing. Yeah. Now let's get into the math a little bit. I'm looking at equation 1 in the paper.
Ah, yes, equation 1.
It approximates the coupling between the transmitter and a specific element on the RIS.
It's a key equation.
But I have to admit, it looks pretty complex.
Yeah, it can seem intimidating at first glance.
Can you walk us through it and maybe break it down?
Of course. So the equation is STX-M is approximately equal to the square root of 1 minus the magnitude of ACM squared times the square root of GTX-GM, ATX-M, divided by 4 pi times DTX-M over lambda times E to the power of negative J2 pi DTX-M over lambda.
Okay, maybe we can break that down piece by piece.
Absolutely, step by step.
So first we have STX-M, right? What exactly does that represent?
So STX-M represents the coupling
The coupling, okay.
between the transmitter, which we denote STX, and a specific element on the RIS. And that specific element, we're calling it the myth element.
Got it.
The term with the square root of 1 minus the magnitude of 3m squared. That takes into account any impedance mismatch.
Impedance mismatch. Now, impedance is like resistance, right?
Kinda, but it's a bit more nuanced. It deals with the opposition to the flow of alternating current, so it involves both resistance and reactance.
Okay, and a mismatch means things aren't quite aligned, so we lose some signal strength.
You got it. And this term in the equation, it helps to ensure we're accounting for any loss in signal strength due to those mismatches on the RIS side. But of course, we're assuming that the transmitter and receiver antennas themselves are perfectly matched.
Right, so we're focusing on the RIS itself. What about that next part of the equation, the one with all the G's and D's?
So that second square root term, that one represents the free space path loss.
Free space path loss, okay.
It basically describes how much the signal weakens as it travels through the air, and it depends on a bunch of factors.
Like distance. I'm guessing distance is a big one.
Distance is definitely key. And that's where DTX-SM comes in.
So DTXM is the distance.
The distance between the transmitter, TX, and our MINth RIS element. But we normalize it by the wavelength.
Normalize it. So divide it by the wavelength of the signal.
Precisely. And lambda, that's our symbol for the wavelength.
Makes sense. What about those Gs? I see GTX and G.
Right. So GTX, that's the gain of the transmitter antenna. Basically, how effectively the transmitter antenna can radiate power in a specific direction.
Okay, so a higher gain means a stronger signal in that direction.
Exactly. Now, G is a bit more interesting.
How so?
Well, Joom represents the gain of the MINth RIS element, but it's not just any gain. It's specifically the gain in the direction of the transmitter.
Ah, so it's how well that specific element on the RIS can receive the signal from the transmitter.
You got it.
Yeah.
And this gain, it's not a constant value. It actually depends on the angle between the MINth element and the transmitter.
Okay, that makes sense. And I see that angle is represented by TXSM.
Right. And here's the thing. To get this gain, we actually need to go back to that initial full wave simulation.
Ah, so that simulation provides this crucial information.
It's a key piece of the puzzle. And then we have that final term in the equation, the exponential one. That one represents the phase shift.
Phase shift arc.
It's the shift in the wave cycle as it travels that distance. And again, we see that distance, DTX-M, normalized by the wavelength.
So the signal doesn't just weaken as it travels, its phase changes too.
Exactly. It's like the wave is shifting slightly in time as it propagates through space, and that phase information is critical when we start talking about how signals from different RIS elements combine.
I'm already starting to see how this one equation is capturing so much of the complexity of how the signal interacts with the RIS. It's like a signal calculator, but super precise.
Precisely. And what's even more remarkable is that this equation allows us to calculate the coupling for any transmitter position without running a new simulation each time.
No, that's efficient. But I'm curious, how do we go from this equation for one element to a complete scatter matrix for the entire system? That's what we ultimately need for optimization, right?
Absolutely. We need to consider all the elements on the RIS and their interactions with both the transmitter and the receiver. And that's where equation 2 comes into play.
Okay, bring on equation 2.
All right, so this equation is a bit more compact in its representation, but it actually packs a lot of information. It basically constructs that entire scatter matrix denoted as S. And this matrix, it's going to be an n plus 2 x n plus 2 matrix.
N plus 2.
Yeah, where n is the number of elements on the RIS. We add 2 to account for the transmitter and receiver.
Ah, so it encompasses the entire system.
Exactly, all the possible couplings within the system. And the equation itself looks like this. S is approximately equal to a big matrix.
Big matrix, lots of information.
Right, and it's made up of smaller submatrices. So we have STX, which is approximately 0, then STTX-RS, and STX-RS, also approximately 0.
Lots of zeros there.
Then on the second row, we have STX-RAS, then SRS, and then SRX-RS.
Okay, keeping up so far.
And lastly, the third row has STX-RX, approximately 0 again, then SPRX-RS, and finally SRX, which is also approximately 0.
All right, so we've got this big matrix filled with smaller matrices. Can you unpack those submatrices a bit? What do they represent?
Certainly. Let's start with STX-RAS.
Okay, STS-RS, what's that one all about?
That one captures the coupling between the transmitter and each element of the RIS. But it's not just any coupling. It's for a given transmitter angle, which we're calling beta.
Ah, so we're factoring in the direction of the transmitter now.
Exactly. And similarly, we have SRX-RSO, which captures the coupling between the receiver and each RIS element. But this time, for a given receiver angle, alpha.
Okay, so we have coupling from the transmitter to the RS and coupling from the receiver to the RS, all neatly organized in those submatrices.
Right. And then we have the heart of it all, the SRS matrix. Remember that one?
Ah, yes. The scatter matrix of the RAS itself, the one they derived from that initial simulation.
Exactly. And then we have the FTX-RX term.
STX-RX. Isn't the whole goal here to establish a non-line of sight link? So the transmitter and receiver can't actually see each other directly.
You're absolutely right. Ideally, STX-RX should be approximately 0 in an NLS scenario. That's what we're aiming for.
But how do they ensure that? In the real world, there are always going to be some stray signals bouncing around.
True, but they took steps to minimize that. For one, they used highly directional horn antennas for both the transmitter and receiver. That helps to focus the signals and reduce any unwanted spreading.
Okay, so like putting blinders on the transmitter and receiver so they only focus on the RIS.
A good way to think about it. And they also employed a clever technique called time gating during measurements.
Time gating, what's that?
It essentially allows them to isolate the signal that's reflected by the RIS. They can filter out any other signals that might have taken a different path, like a direct path between the transmitter and receiver.
So they're making sure they're only measuring the true impact of the RIS.
Exactly. It's all about clean, accurate measurements. And those zeros in the matrix for STX-RX, they tell us that their approach worked.
They effectively minimized any direct coupling. Impressive. So we've got this elegant far-field approximation. We can build the complete scatter matrix. They actually put it to the test.
Oh, absolutely. They designed a real physical RIS.
Hold on, they actually built one.
They did. A small one, mind you.
Okay, what do we mean by small?
They went with 7x2 elements.
7 by 2 elements.
Yeah, operating at a frequency of 3.55 gigahertz.
That's 3.55 gigahertz, got it.
And they placed both the transmitter and receiver 2 meters away from the RIS. The goal was to optimize the RIS for a receiver at an angle of alpha equals 0 degrees.
Alpha equals 0 degrees, okay.
With the transmitter positioned at an angle of beta equals 30 degrees. So basically, they wanted to find those reactance values for each RIS element that would maximize the signal strength at the receiver coming from that specific transmitter location.
Okay, so they had a clear objective.
Exactly.
And I'm guessing they ran this optimization using both their fancy new approximation method and a full simulation for comparison. How did the results stack up?
Well, if you look at figures 2b and 2c in their paper, you'll see those optimized capacitance values for each RIS element.
Capacitance values, all right.
And the remarkable thing is, those values from their approximation, they are incredibly close to the values from the full simulation.
No way. That's incredible.
It is. It's a huge win for their method, because it means it can achieve accurate results without all that computational burden of a full simulation.
They're getting the same level of accuracy, but much faster. That's impressive.
It's a testament to the power of this approximation. Now, I'm sure our listeners are wondering how those capacitance values actually translate into building a real RIS.
Yeah, how do you go from numbers on a page to a physical device?
Well, in their physical implementation, they used varactor diodes.
Varactor diodes, I've heard of those. They're like voltage-controlled capacitors, right?
Exactly. Electronic components where you can actually tune the capacitance.
Tune it by changing the voltage applied across it.
Precisely. And that's what makes them so useful for RIS. You can dynamically adjust the reactance of each element by simply changing the voltage.
So they essentially created a little mini circuit for each element on the RIS, with a varactor diode that could be tuned to the desired capacitance.
Exactly. It's a pretty clever setup. Now, there was one practical constraint they had to deal with.
What was that?
The varactor diodes they used, they had a limited capacitance range.
Ah, so they couldn't just pick any arbitrary value.
Right. But thankfully, the range was sufficient to accommodate those optimized values they had obtained.
That's good news. So they optimized the design, built it with real components, and it actually worked.
It did. They measured the bistatic radar cross-section, which it basically tells you how well the RIS reflects the signal in the desired direction.
Okay, and the results?
The results are shown in figure 3c in their paper. And it's really remarkable. Those BRCS curves from their approximation method, the full simulation, and the actual measurements from their physical RIS, they're all incredibly close.
No way. So not only was their approximation accurate compared to the simulation, but it also matched the real-world performance of their physical RIS.
Precisely.
Yeah.
And that's a really strong validation of their entire approach.
That's fantastic. I'm looking at figure 3c right now, and I see curves for the RIS, but there's also one labeled reflector. What's the purpose of that?
Ah, yes, the reflector. That's a plain copper reflector of the same size as the RIS. It acts as a reference point.
A reference point. Okay.
It helps illustrate the impact of the RIS, compared to just a simple reflector that just bounces the signal back without any intelligent manipulation.
Okay, so it's like a baseline.
Exactly. It helps us to see the improvement achieved by the RIS.
And how much of an improvement are we talking about here?
Well, even this small 7x2 element RIS achieved a significant gain, exceeding plus 15 dBs at the target receiver angle.
Plus 15 dB, that's huge.
It really highlights the potential of this technology even at a small scale.
Wow, this is all so fascinating. Okay, before we move on, I just want to do a quick recap. We've got this research team. They've developed a far-field approximation method that really slashes the time it takes to optimize RIS designs.
And without sacrificing accuracy.
Exactly. And they've proven it not just through simulations, but by actually building and testing a real physical RIS.
Bridging that gap between theory and practice.
It's a major step forward in making RIS a practical reality. This is truly groundbreaking stuff.
It opens up so many possibilities for the future of wireless communication.
It really does. But before we delve into those possibilities, let's take a closer look at that initial simulation they used to kick things off. What's happening in that simulation, and what information are they extracting from it?
Right, that initial simulation is crucial. It all comes down to the SRIS matrix, the scatter matrix of the RIS itself. This matrix essentially captures how each element on the RIS interacts with every other element.
So they're simulating the RIS in isolation before even bringing the transmitter and receiver into the picture.
Precisely. It's about understanding the intrinsic behavior of the RIS before we introduce the complexities of the transmitter and receiver.
Makes sense. Now, they mentioned using the multi-level fast multipole method, or MLFMM, for these simulations. Why that specific method?
Well, MLFMM is a very powerful computational electromagnetic technique. It's particularly well suited for handling complex structures with many interacting elements, like our RIS. It's known for its efficiency and accuracy, especially when you're dealing with what we call electrically large problems.
And RIS often falls into that category.
It can get quite large, yes. So you need a robust and efficient simulation method like MLFMM to handle the complexity.
Okay, so they're using a top-notch tool to make sure that initial simulation is as accurate as possible. Now, I'm picturing this SRIS matrix. What does it actually look like?
Imagine a grid where each row and column represents an element on the RIS.
Okay, I'm picturing it. So if you have an n-element RIS, you have an n by n matrix.
Exactly. And each entry in this matrix, let's say SRI mount n, it represents the coupling between the mth element and the nth element of the RIS.
So it's like a map of how every element on the RIS is communicating with every other element.
That's a great way to visualize it. And the values in this matrix, they can be complex numbers.
Complex numbers, not just simple magnitude.
Right, complex numbers, because we need to capture both the magnitude and the phase of the coupling. The magnitude of the complex number that represents the strength of the coupling, and the angle of the complex number that represents the phase shift introduced by the interaction between those two elements.
Ah, the phase shift comes back into play. So we're not just looking at how strongly the elements are coupled, but also how their signals align in time.
Precisely. That phase information is crucial.
Okay, I'm starting to grasp the level of complexity here. And this is all happening within the RIS itself, even before we factor in the transmitter and receiver.
Exactly, but here's the beauty of it. Once you have that SRIS matrix, you've captured the fundamental behavior of the RIS.
It's like the RIS's fingerprint, in a way.
I like that analogy. And from there, you can use those equations we discussed earlier, equation 1 and equation 2, to extrapolate and predict how the RIS will interact with the transmitter and receiver from any position.
Wow, so that initial simulation does a lot of heavy lifting.
It front-loads the complexity, and then the far-field approximation steps in to handle the rest much more efficiently.
It's like a 1-2 punch for efficient RIS optimization.
Precisely. And the results speak for themselves.
They really do. Now, you mentioned that the elements in that SRIS matrix can be complex numbers. Why is that? What does the phase information tell us?
That's a great question. Remember, we're dealing with waves here, electromagnetic waves. And waves, they have this interesting property. They can interfere with each other.
Right, like constructive and destructive interference.
Exactly. If two waves arrive at the receiver in phase, they reinforce each other, creating a stronger signal.
But if they arrive out of phase,
then they can actually cancel each other out, leading to a weaker signal. And that's why the phase information is so important. It determines how those signals from different elements on the RIS will ultimately combine at the receiver.
So the RIS isn't just reflecting signals, it's intelligently manipulating their phase to ensure they combine constructively.
Exactly. It's about orchestrating those waves to maximize the signal strength at the receiver. And that's the real power of RIS.
It's like a tiny conductor leading an orchestra of electromagnetic waves. It's amazing. Now, I want to talk more about those real-world measurements they conducted. They used varactor diodes to control the reactance of each RIS element. Can you tell us a bit more about how those work?
Sure. A varactor diode is a special type of diode, and the key feature is that its capacitance can be controlled.
Controlled how?
By varying the voltage applied across it. Essentially, it acts as a voltage-controlled capacitor.
So you can tune the capacitance by simply changing the voltage.
Exactly. And this tunability is what makes varactor diodes so appealing for RIS applications. It allows you to dynamically adjust the reactance of each RIS element.
And that dynamic adjustment is key for optimizing the signal reflection rate.
Precisely. By changing the voltage applied to each varactor diode, they can fine-tune the phase of the signal reflected by that element.
Okay, so they're not just setting a fixed capacitance, they're dynamically controlling it.
Right. And by carefully coordinating the voltages across all the varactor diodes on the RIS, they can achieve we call beamforming.
Beamforming, right?
It's essentially focusing the energy of the reflected signal in a specific direction, and that's essential for maximizing signal strength and coverage.
So it's like they're creating these invisible beams of signal that they can steer and shape.
That's a good way to think about it. And it all comes down to controlling those tiny varactor diodes.
Amazing. But how do they actually implement this in their physical RIS? What did that setup look like?
They essentially built a small circuit board.
A circuit board, okay.
And on this board, each RIS element was connected to its own varactor diode.
So a one-to-one mapping.
Exactly. And then they used a microcontroller.
A microcontroller, like a tiny computer brain.
Yes. It allowed them to control the voltage applied to each diode individually, so they could precisely set those desired capacitance values.
So they had this tiny computer controlling an army of miniature adjustable antennas. It's incredible.
It is a pretty remarkable setup, and the fact that they achieved such accurate results with a relatively simple design, it speaks to the power of this approach. Now, it's worth noting that varactor diodes aren't the only game in town.
Oh. Are there other technologies being explored for controlling the reactance of RIS elements?
Absolutely. It's an active area of research. While varactor diodes are popular, they do have some limitations, so researchers are always looking for alternatives that might offer even better performance or more flexibility.
Like what? What are some of the technologies on the horizon?
Well, one promising area is microelectromechanical systems, or MEMS. These tiny devices can physically move or deform structures at a microscopic scale.
Tiny moving parts, wow.
Exactly. Imagine tiny MEMS switches that can connect or disconnect different parts of the RIS elements, allowing for very abrupt changes in reactance, potentially even faster than what you can achieve with varactor diodes.
So instead of just tuning the capacitance, you could essentially turn parts of the RIS element on or off?
Precisely. And that level of control, it could open up some really exciting possibilities for beamforming and signal manipulation. We could achieve even more precise control over those wireless signals.
Wow, that sounds powerful. Any other contenders in the RIS technology race?
Another exciting area involves materials.
Material.
Yes, materials with properties that can be dynamically changed. Properties like permittivity or permeability.
Okay, and how do you change those properties?
You can do it using external stimuli like light or temperature. So imagine a material that becomes more or less reflective depending on how much light it's exposed to.
That's wild. It's like the RIS itself is changing its properties on demand.
Exactly. And these material-based approaches, they have some unique advantages. They could be faster than mechanical systems, they might consume less power, and they could even lead to more compact RIS structures.
So we could build RIS that are more seamlessly integrated into the environment.
Exactly. It's all about pushing the boundaries of what's possible.
This is also fascinating, but let's bring it back to the research we're focusing on today. We've covered the simulations, the hardware, and even touched on the broader landscape of RIS technologies. But I want to hear more about the actual results of their measurements. What did they observe when they put their physical RIS to the test?
That's where the real excitement lies. Remember that bistatic radar cross-section plot we talked about earlier?
The BRCS plot. Yep.
That plot shows very clearly that their physical RIS, the one they built, it actually performed almost exactly as predicted.
So both their far-field approximation and the full-wave simulation were spot on.
They were, and that's huge. It means this method could significantly accelerate the design and optimization of RIS for a whole range of applications.
Imagine being able to rapidly prototype and test different RIS designs without waiting for those long, drawn-out simulations.
It could revolutionize how we develop and deploy RIS technology. We could see a much faster adoption of RIS across many industries.
That's exciting. Now, the authors also highlighted the impact that even their small 7x2 element RIS had on signal strength. They saw that gain of over 15 dB, right?
Yes, over 15 dB at the target receiver angle, a remarkable improvement.
And this is just with a small RIS. Imagine what we could achieve with larger, more sophisticated arrays.
The potential is truly mind-boggling. It's an incredible time to be working in this field.
It really is. But before we get too carried away dreaming about the future, I want to shift gears a bit and discuss the broader implications of this research. What does this faster optimization process mean for the future of RIS development and deployment? What doors does it open?
That's a great question, and it gets to the heart of why this research is so significant. I think one of the most immediate implications is the potential for rapid prototyping and experimentation. Imagine being able to quickly design and optimize RIS for very specific applications.
Without being held back by those time-consuming simulations.
Exactly. And that speed, that agility, it's crucial in today's tech landscape. Companies and research groups are in a race to bring RIS-enabled products and services to market.
It's a competitive field.
Very competitive. And this research, it gives them a powerful tool, a tool that lets them explore a much wider range of possibilities in a fraction of the time.
So it's like handing engineers a superpowered design tool. I like it.
And with that tool, I think we can expect to see a much faster adoption of RIS across various industries.
Okay, I can already envision a world where RIS is everywhere, seamlessly integrated into our buildings, vehicles, maybe even our clothing.
It's not that far-fetched. The potential is there.
It's incredible. But let's get specific. Can you give us some concrete examples of how this faster optimization process could impact real-world applications?
Sure, let's start with something we're all familiar with. Poor cellular coverage. Imagine those areas where it's notoriously difficult to get a good signal.
Like underground tunnels or remote rural locations? Been there, done that.
Exactly. Those are prime candidates for RIS deployment. And with this faster optimization method, we could tailor the RIS design to the specific geometry and characteristics of those environments. We could maximize signal strength and coverage exactly where it's needed most.
So instead of just building more cell towers, which can be expensive and sometimes just not feasible, we could strategically place RIS to precisely target those coverage gaps.
Precisely. It's a much more elegant and efficient solution.
I love it. And I bet this rapid optimization would be especially valuable in those environments that are constantly changing, like a busy airport or a crowded stadium where people are moving around and the wireless demands are shifting all the time.
Absolutely. In those dynamic scenarios, the RIS needs to be able to adapt. It needs to adjust its configuration on the fly to keep up with those changing user locations and traffic patterns.
It's like the RIS needs to think on its feet.
In a way, yes, and this faster optimization method allows for that. It allows the RIS to almost learn the environment and adapt in real time.
So we're moving closer to that vision of a self-organizing, self-healing wireless network.
Precisely. And that has enormous implications for reliability and efficiency. Now, we've talked about coverage, but what about speed?
Right, because everyone wants faster data rates.
Yeah.
Can RIS deliver on that front?
Absolutely. Remember those highly directional beams we talked about earlier?
The ones the RIS creates through beamforming.
Exactly. Those beams can be used to focus the energy of the signal towards the intended receiver.
Yeah.
And this focusing, this concentration of energy, it can significantly increase the signal strength at the receiver, which of course translates to higher data rates.
So it's like creating a dedicated high-speed lane for your signal, free from all that interference from other devices competing for bandwidth.
That's a great way to put it. And this faster optimization method we've been discussing, it allows you to tailor those beams with incredible precision, ensuring maximum throughput, even in those really densely populated, high-traffic environments.
It's like having a personal signal booster wherever you go. I like
It's
it.
a powerful concept. And RIS is really opening up a lot of possibilities in that realm.
Okay, so we've talked about coverage, we've talked about speed, both critical aspects of wireless communication, but I feel like we're just scratching the surface here.
I agree.
Are there any more like futuristic applications that RIS might enable? I'm talking about those almost out there ideas that this technology could unlock.
Oh, absolutely. And that's where things get really exciting. One area that holds immense potential is wireless power transfer.
Wireless power, whoa, like beam energy through the air.
Exactly. Imagine using RIS to beam energy to power devices without any wires, safely and efficiently.
Okay, now that is futuristic. So instead of plugging in my phone or even my electric car, I could just park it near an RIS and it would start charging.
That's the vision. And this faster optimization method, it would be crucial for that application.
How so?
Well, we need to ensure that the power transfer is highly targeted and efficient.
Right, we don't want energy being wasted or beamed in the wrong direction. Safety first.
Exactly. RIS optimization plays a crucial role in addressing those concerns.
Okay, wireless power, that's pretty mind-blowing. Anything else on your futuristic RIS application list?
How about holographic communication?
Whoa, hold on, like Star Wars holograms.
Exactly. Think about it. RIS could be used to manipulate those electromagnetic waves in such a way that they create 3D holographic projections.
That's incredible. So instead of just seeing a flat image on a screen, You can have a virtual meeting where it feels like the person is actually in the room with you.
Exactly. Or imagine holographic entertainment experiences, truly immersive, 3D visuals all around you. The possibilities are endless.
It sounds like something straight out of science fiction. But with RIS, it's becoming science fact.
It is, and it's just the beginning. As this technology matures and as researchers continue to push those boundaries, I think we're going to see even more groundbreaking applications emerge. It's a really exciting time to be following this field.
I'm completely with you on that. It's mind-blowing to think about the potential impact of RIS. But let's not get ahead of ourselves.
Right, back to the research at hand.
For now, I just want to say a huge thanks to our expert for guiding us through this deep dive. It's been a fascinating journey into the world of RIS.
The pleasure was all mine. Always happy to talk about this groundbreaking technology.
And to all our listeners, thank you for joining us. Keep your eyes on RIS because the future of wireless is intelligent, adaptable, and it's closer than we think. Until next time, keep exploring, keep learning, and keep diving deep into the world of cutting-edge tech.
It can significantly increase the signal strength at the receiver, which of course translates to higher data rates.
So it's like creating a dedicated high-speed lane for your signal, free from all that interference from other devices competing for bandwidth.
That's a great way to put it. And this faster optimization method we've been discussing, it allows you to tailor those beams with incredible precision, ensuring maximum throughput, even in those really densely populated, high-traffic environments.
It's like having a personal signal booster wherever you go. I like
It's
it.
a powerful concept. And RIS is really opening up a lot of possibilities in that realm.
Okay, so we've talked about coverage, we've talked about speed, both critical aspects of wireless communication, but I feel like we're just scratching the surface here.
I agree.
Are there any more like futuristic applications that RIS might enable? I'm talking about those almost out there ideas that this technology could unlock.
Oh, absolutely. And that's where things get really exciting. One area that holds immense potential is wireless power transfer.
Wireless power, whoa, like beam energy through the air.
Exactly. Imagine using RIS to beam energy to power devices without any wires, safely and efficiently.
Okay, now that is futuristic. So instead of plugging in my phone or even my electric car, I could just park it near an RIS and it would start charging.
That's the vision. And this faster optimization method, it would be crucial for that application.
How so?
Well, we need to ensure that the power transfer is highly targeted and efficient.
Right, we don't want energy being wasted or beamed in the wrong direction. Safety first.
Exactly. RIS optimization plays a crucial role in addressing those concerns.
Okay, wireless power, that's pretty mind-blowing. Anything else on your futuristic RIS application list?
How about holographic communication?
Whoa, hold on, like Star Wars holograms.
Exactly. Think about it. RIS could be used to manipulate those electromagnetic waves in such a way that they create 3D holographic projections.
That's incredible. So instead of just seeing a flat image on a screen, you can have a virtual meeting where it feels like the person is actually in the room with you.
Exactly. Or imagine holographic entertainment experiences, truly immersive, 3D visuals all around you. The possibilities are endless.
It sounds like something straight out of science fiction. But with RIS, it's becoming science fact.
It is. And it's just the beginning. As this technology matures and as researchers continue to push those boundaries, I think we're going to see even more groundbreaking applications emerge. It's a really exciting time to be following this field.
I'm completely with you on that. It's mind-blowing to think about the potential impact of RIS.
It really is transformative.
A huge thanks to our expert for guiding us through this deep dive. It's been a fascinating journey into the world of RIS.
My pleasure. I always enjoy discussing these cutting-edge technologies.
And to all our listeners, thank you for joining us. Keep your eyes on RIS because the future of wireless is intelligent, adaptable, and it's closer than we think. Until next time, keep exploring, keep learning, and keep diving deep into the world of cutting-edge tech. Hey everyone, welcome to another deep dive. Today we're going to be talking about something pretty fascinating, something that's got a lot of buzz around it. I'm talking about reconfigurable intelligent surfaces.
Yeah, these RIS, as they're called.
Yeah, RIS, exactly. They're like, smart mirrors for wireless signals. And they hold this incredible potential, right, to completely change the way we think about coverage and speed in wireless communication, but optimizing them, finding that sweet spot where they perform their best. Well, that's where things get a little bit tricky.
Yeah, it's no walk in the park, that's for sure. Simulating all those possible scenarios to find the perfect setup for your RIS, it's computationally demanding.
It's a real-time sync, and it just eats up so much computing power. So what can we do about it?
Well, that's the problem that this paper by Lang and the team is trying to address. They're proposing a far-field approximation technique, basically a clever way to extrapolate data from just a single simulation. And the idea is to use that data to predict how the RAS performs in all sorts of different situations.
Okay, so it's like a shortcut. Instead of running tons of simulations, you just do one and then use this approximation to fill in the blanks. That sounds promising, but I'm always a little skeptical of shortcuts. They often come with trade-offs. So I'm curious, how well does this actually work?
Yeah, that's the million-dollar question, isn't it? Does it sacrifice accuracy for efficiency?
Well, let's find out. First, let's get everyone on the same page. Let's talk about the basic setup of a typical RIS-aided wireless communication link. I think figure 1 in the paper does a good job of illustrating this.
Absolutely. So you've got your transmitter, right, sending out the signal, and you've got your receiver waiting to pick it up. But there's no direct line of sight between them.
So that's where the RIS comes in, right?
Exactly. The RIS is strategically placed to bounce the signal from the transmitter to the receiver.
It's not just a simple mirror, though. It's more like a relay station that can actually manipulate the signal, right? And this is where that scatter matrix comes into play.
The scatter matrix is essentially the heart of the system. It's a mathematical representation of how the RIS interacts with the incoming signal. It characterizes the whole system's behavior. But, and here's the rub, simulating this matrix for every possible position of the transmitter and receiver. That's what really bogs things down computationally.
Got it. So that's the problem they're trying to solve.
Wow.
Because how does this far-field approximation actually work? How did they get around having to simulate all those different scenarios?
Well, they've come up with this equation 1, which estimates the coupling between the transmitter and each element on the RIS. And they do this by using parameters that are easy to measure or calculate, like the antenna gains and the distances involved.
Okay, so walk me through this equation a bit. What's the underlying principle here?
The key idea is that when you're far enough away from the RIS, the signal wavefronts can be approximated as plane waves. It's a simplification, but a powerful one. It allows them to treat the non-line-of-sight link as a series of lossy two-ports, each with its own delay.
Lossy two-ports. I remember you mentioned that before. Could you just remind us what that means in this context?
Of course. So a two-port network is essentially a component with an input and an output. And lossy just means that some of the signal energy is inevitably lost during transmission.
Okay, makes sense. So equation 1 gives you the coupling for a single element on the RIS. But we need to account for the entire surface, right? How do they do that?
That's where equation 2 enters the picture. It combines all those individual coupling terms, calculated using equation 1, to build the complete scatter matrix, which they denote by S.
All right, so they're essentially taking a divide and conquer approach. Calculate the individual couplings, then stitch them together to get the big picture. But how do they actually know if this approximation is any good?
They put it to the test. They designed a specific RIS, a small one with 7x2 elements, operating at 3.55 gigahertz. And they were very careful with their measurements, using horn antennas to minimize interference and a technique called time gating to isolate the signal they were interested in. You can see all this in figure 2A.
So horn antennas, time gating, these are all about getting clean, accurate measurements, right? So what did they find? Did the approximation hold up?
Well, they compared the optimized capacitance values for each element on the RIS obtained through their approximation with those from a full simulation. And take a look at figures 2B and 2C. The results are strikingly similar.
Wow, so the approximation actually predicts the optimal configuration of the RIS pretty accurately. That's impressive. But this is still just a simulation environment. Does this translate to the real world?
That's the ultimate test, isn't it? And that's what they tackled next. They actually built a physical RIS using varactor diodes to achieve the desired capacitance range.
Varactor diodes, those are pretty neat little components, aren't they? So they actually built the thing. But how did they measure its performance in a real-world setting?
They used a metric called the bistatic radar cross-section, or BRCS, which tells you how effectively the RIS is redirecting the signal towards the receiver. And here's the kicker. The BRCS values predicted by their approximation, the full simulation, and the actual measurements from the physical RIS all showed remarkable agreement. You can see that in figure 3C.
Hold on, let me make sure I understand this. They took this shortcut, this approximation method, and it actually worked. They used it to optimize the RIS, built the physical device, and it performed as predicted in a real-world scenario.
It did. It's pretty remarkable, and it opens up all sorts of possibilities for developing and deploying RIS technology much faster and more efficiently.
That's amazing. But let's not get too carried away just yet. This was a relatively small RIS with specific components and operating at a specific frequency. We need to understand the limitations of this research before we declare it a complete game changer.
You're absolutely right. Further research is definitely needed to see if this approximation holds up for larger, more complex RIS designs with different element types and arrangements.
Okay, so there's still more to explore, but even with those limitations, this is a pretty exciting development, wouldn't you say?
Absolutely. It's a step in the right direction, and it shows that there are clever ways to optimize RIS without getting bogged down by those computationally intensive simulations.
This has been a great overview, but I think we need to dig a bit deeper into the math behind this approximation, don't you?
I agree. Understanding the details of equation 1 and how it captures those far-field interactions, that's crucial. And then we can talk about those experimental choices, like the specific frequency and the type of diodes they used.
Sounds like a plan. Let's roll up our sleeves and get into the nitty-gritty. All right, welcome back, everyone. Let's dive back into this far-field approximation stuff. Last time, we kind of skimmed over it. I think it's time to, really roll up our sleeves and dig into the math a little bit. Where we left off was looking at equation 1. This is where the magic happens, right?
Yeah, this is the heart of it. Equation 1 might seem a bit intimidating at first glance, but it's actually quite elegant in how it captures those far-field interactions.
Elegance in math. Now you're speaking my language. Break it down for me. What's going on here?
Well, the core idea is that they're exploiting the principles of far-field analysis. When you're far enough away from the RIS, those complex wavefronts coming from the transmitter essentially start to look like plane waves.
Right, yeah, we talked about that simplification before.
Exactly. And this simplification is what allows them to model the interaction between the transmitter and each element on the RIS as a straightforward two-port network.
Okay, the lossy two-port concept. Got it. But how does that translate into this equation? I'm looking at it now, and there are antenna gains, distances, this exponential term. It's a bit much.
Let's unpack it. So you've got the antenna gains. Those represent how effectively both the transmitter and the element on the RIS focus the signal. Then you've got the distance between them. That obviously plays a role in the strength of the signal. And finally, you've got that exponential term, which captures the phase shift that the signal experiences as it travels that distance.
Ah, right, the phase shifts. So it's not just about the strength of the signal, but also about how the peaks and troughs of the wave align when they reach the RIS.
I see. Exactly. It's all about wave interference. And the beauty of this equation is that all those parameters are readily available. You don't need to run complex simulations to get them. It's based on the physical characteristics of your setup.
So that's where the efficiency comes in. They've essentially found a way to bypass those time-consuming simulations by leveraging this simplified far-field model.
Exactly. And remember, this equation gives you the coupling for just one element on the RIS. To get the complete picture, we need equation 2, which combines all those individual coupling terms to build the entire scatter matrix.
Right, the scatter matrix, which we were calling the personality of the RIS. But I'm still a little hung up on the accuracy. I mean, simplification is great, but are we sacrificing too much accuracy for the sake of efficiency?
That's a fair question. And the paper addresses this directly by comparing the results of their approximation with those from full wave simulations. And what they found was, for the specific RIS design and scenario they tested, the approximation was remarkably accurate. And they didn't stop there. They actually built a physical RIS and tested it in a real-world setting.
Right, yeah, we talked about those measurements with the static radar cross-section and how well they lined up with the predictions from the approximation.
Exactly. So it's not just a theoretical exercise. It actually works in practice.
That's pretty convincing. Okay, so we've established that this approximation works really well. But before we get too carried away with the possibilities, I want to go back to some of the details of their experimental setup that I found intriguing. First off, the fact that they chose to operate at 3.55 gigahertz, was that just an arbitrary choice? Or was there a reason behind it?
It was a very deliberate choice. The thing about higher frequencies is that they offer more bandwidth, which means you can potentially transmit data much faster.
Oh, right. So that's why everyone's so excited about 5G and millimeter wave frequencies. Higher frequency equals faster speeds. Got it. But I imagine there are downsides as well, right?
There are always trade-offs. Higher frequencies tend to attenuate more quickly, meaning the signal weakens faster as it travels through the air, and they can also be blocked more easily by obstacles.
Ah, I see. So they're playing a balancing act here. They want a frequency high enough to get those speed benefits, but not so high that the signal becomes unusable.
Exactly. 3.55 gigahertz seems to be that sweet spot. High enough to demonstrate the benefits of RIS, but not so high that it introduces too many challenges.
Makes sense. Okay, now another thing that caught my attention was their choice of varactor diodes to actually build the RIS. Why those specific diodes? What makes them so special?
Repeater diodes are cool because you can adjust their capacitance by changing the voltage applied to them.
So they're like tiny little tunable capacitors?
Precisely. And that's what makes them so perfect for RIS. By adjusting the voltage on each diode, you can fine-tune the capacitance of each element on the RIS, which in turn affects how it interacts with the incoming signal.
Oh, I see. So it's like having a bunch of little knobs that you can tweak to control how the RIS shapes and directs the signal.
You got it. And that's what allows you to optimize the performance of the RIS for different scenarios and channel conditions.
That's amazing. But I imagine figuring out the optimal settings for all those diodes is no easy feat.
You're right. It's a complex optimization problem. But that's where the power of this far-field approximation comes in. Instead of running those time-consuming full-wave simulations for every possible configuration, they can leverage this simplified model to quickly explore a wide range of settings and find the optimal ones.
So it's not just a theoretical curiosity. It's a practical tool that can actually accelerate the development and deployment of RIS technology. This is where it gets really exciting, I think. We've been focusing on the technical details, but what I'm really interested in is the impact this could have on the future of wireless communication.
Right. It's about more than just equations and simulations. It's about changing the way we connect with the world.
Exactly. But before we get carried away with those future possibilities, I think it's worth taking a step back and looking at the big picture. What are the key takeaways from this research, and what are some of the limitations that we still need to keep in mind?
Good point. Let's summarize what we've learned so far and consider what else needs to be explored.
All right, so for everyone listening, let's recap the most important points about this far-field approximation technique. So to recap, we've learned that this far-field approximation technique basically uses a simplified model of how signals behave when they're far away from the RIS.
Right. It treats those interactions as lossy two-port networks.
And the beauty of that is they can estimate those crucial parameters without having to run those super complex full-wave simulations over and over again for every single scenario.
Right. It saves a ton of time and computing power.
And the best part is they actually backed up their approach with both simulations and real-world measurements.
Yeah, the results they got lined up incredibly well with the actual performance of their physical RIS.
But we do need to remember that this was all validated for a specific type of RIS and in a controlled environment.
Definitely. More research is needed to see if this approximation method holds up for larger, more complex RIS designs and in more challenging real-world situations.
Okay, fair enough. But even with those limitations, this is still a pretty exciting development, don't you think?
Oh, absolutely. It's a huge step forward.
I mean, we've been talking about the technical nuts and bolts here, but what really gets me going is imagining how this could change the way we experience wireless communication.
Right. It's about the real-world impact, not just the theory.
Imagine a world with no more dead zones. Never dropping a call in an elevator or struggling to get a decent signal in that one corner of your house.
It's a pretty enticing vision, isn't it? Seamless connectivity everywhere you go.
And it's not just about coverage either. Think about all the places where tons of people are trying to connect at the same time, like a crowded stadium or a concert. Imagine if everyone could easily stream high-definition video without any lag or buffering.
That would be a game changer for sure.
And it all comes down to the RIS, right? By shaping and directing the signals, it can bypass those obstacles and congestion issues. And we haven't even talked about the security and privacy implications. Didn't they mention that RIS could potentially improve those aspects as well?
Yeah, they did. With traditional wireless systems, your signal is basically being broadcast in all directions, which means anyone within range could potentially intercept it.
Right, even if they're not supposed to.
Exactly. But with RIS, you can create highly focused beams, sending the signal only to the intended receiver.
So it's like creating a private, secure channel for your data. That's pretty cool.
And you can even go a step further and use RIS to intentionally scramble the signal in certain directions.
So it's like a shield protecting your data from eavesdroppers. That's impressive.
It has huge implications for wireless security and privacy, especially as we become even more reliant on wireless connectivity for things like banking and healthcare.
Yeah, the stakes are getting higher, so better security is crucial. Oh, we also touched on the energy efficiency aspect. Didn't they say something about RIS being able to reduce power consumption?
Yeah, because you're only sending the signal where it needs to go. You're not wasting energy broadcasting it in all directions.
So it's better for the environment and could potentially even save us some money on our energy bills. Win-win. So we're potentially looking at faster speeds, wider coverage, enhanced security, and a greater energy efficiency, all thanks to RIS. It's pretty mind-blowing when you think about it.
It's definitely a game changer. But as with any new technology, there are still challenges to overcome.
Right, we've talked about some of the limitations of the current research. We need to see how this approximation method works for bigger and more complex RIS systems. What other hurdles are out there?
Well, scalability is a big one. The experiments in this paper focused on a relatively small RIS, but for real-world applications, we'll need to figure out how to manufacture much larger surfaces, potentially with thousands of elements.
Yeah, scaling things up is always tricky, and controlling all those elements must be pretty complex as well.
Definitely. You need very sophisticated algorithms to optimize the settings for each individual element, and those algorithms need to be able to adapt to changing conditions and multiple users.
So it's a combination of hardware and software challenges. It'll take some clever engineering and some powerful algorithms to make this all work smoothly.
Absolutely. It's a truly interdisciplinary effort, which makes it all the more interesting.
It's exciting to think about all the brilliant minds out there who are working on making this technology a reality. This research could be the catalyst for a whole new wave of innovation in wireless communication.
I agree. It's a really promising area of research.
And it all comes down to this fundamental idea of being able to shape and control wireless signals with the same precision that we control light. It's a paradigm shift that could transform how we connect with the world around us.
It's a vision worth pursuing.
Well, folks, that's our deep dive into the world of reconfigurable intelligent surfaces. We hope you enjoyed it. Until next time, keep exploring and stay curious. Welcome to the Deep Dive. Ready to jump into some cutting-edge wireless tech with me today?
Always up for a deep dive, especially when it involves something as promising as reconfigurable intelligent surfaces.
RIS, for short. It's a mouthful. But from the research you send over, this tech could really be a game changer.
Absolutely. It has the potential to transform wireless communication as we know it. Imagine a world with no more dead zones. Just seamless, super fast connectivity everywhere.
Sounds like a dream come true, especially in my old house, where I had a Wi-Fi dead zone right in my office.
Yeah.
But let's get real for a sec. The material you sent over, all this research on RIS optimization, it gets pretty heavy into the math, right?
Yeah, optimizing these surfaces is no walk in the park. It involves a lot of complex calculations, especially when it comes to simulating how they behave in different scenarios. But that's what makes this particular research so exciting.
Oh, okay. Why is that?
Well, it proposes a really clever technique, a way to streamline those complex calculations using something called far-field approximation. It's a way to make the optimization process much more efficient without sacrificing accuracy.
Streamlining and efficiency, those are words I like to hear. But before we get too deep in the weeds, let's make sure we're all on the same page. Could you give us a quick refresh on what RIS actually is? For those of us who haven't been living and breathing this stuff for the past few months.
Sure. At its core, an RIS is essentially a surface covered in these tiny antennas that can manipulate the direction and strength of wireless signals. Think of it like a smart mirror that can reflect and focus those radio waves to improve connectivity.
So instead of signals bouncing around randomly, an RIS can actually steer them to where they need to go. Pretty clever.
Exactly. But the challenge is that each of those tiny antennas needs to be carefully configured to maximize the performance of the whole system. And figuring out that optimal configuration, well, that's where all those complex simulations and heavy-duty math come into play.
Got it. So we need to determine the perfect settings for every single antenna to squeeze out the best possible performance from the whole RIS. Sounds like a computational nightmare.
It can be. Traditional approaches involve running those complex simulations, modeling how signals interact with the RIS in tons of different scenarios. It's time-consuming and computationally expensive, but that's where this concept of far-field approximation comes in.
Okay, now we're getting to the heart of the matter. Lay it on me.
Yeah.
What is this far-field approximation, and how does it help simplify things?
So the basic idea is this. When you're far enough away from an antenna, the electromagnetic waves, they start to look a lot like plane waves. It's a simplification for sure, but it's one that holds up surprisingly well in many practical situations.
And why is that simplification so important?
Well, by assuming plane waves in the far field, we can drastically simplify those calculations needed to describe how the RIS behaves. No more dealing with those complicated wavefront curvatures. It's like trading in a super complex equation for something much more manageable.
So it's a shortcut, but one that's grounded in the actual physics of how electromagnetic waves propagate. I like it. But this paper takes it a step further, right? They don't just talk about the concept, they actually put it into practice.
Right. They actually crunch the numbers and demonstrate how this far-field approximation works in a real-world scenario. They start by looking at how a signal from a transmitter couples with a specific element on the RIS. And that's where equation 1 in the paper comes in.
Okay, time to put on our math hats. Equation 1. It's basically a formula that describes the signal strength at a particular point on the RIS.
Yeah, got it. And what's interesting is how this equation subtly incorporates the far-field approximation. It's all in that exponential term, the e to the power of negative j2 pi dtx-m over lambda.
Okay, break that down for me. What's going on in that exponential term?
Well, that term represents the phase shift that the signal experiences as it travels from the transmitter to that specific element on the RIS. Think of phase shift as the relative position of the peaks and troughs of a wave.
So as the wave travels that distance, its shape changes slightly, and this term captures that change.
Exactly. And the key is that by using that exponential term, we're implicitly assuming that the wavefronts are nice and planar by the time they reach the RIS. That's the magic of the far-field approximation at work.
It's a sneaky simplification, but it seems to be working. Now, once we know the signal strength at each element on the RIS, what's the next step? How do we use that information to optimize the entire system?
That's where equation 2 steps into the spotlight. It introduces us to the scattering matrix, which is basically a matrix that describes how the entire RIS system responds to an incoming signal.
A matrix. So we're talking rows and columns of numbers, each representing what exactly?
Well, each entry in the matrix, it tells you how the signal bounces between two specific elements on the RIS. So it's like we're building a map of all the interactions happening on that surface.
A map of signal interactions. Interesting. And how does this scattering matrix tie back into that far-field approximation we were talking about?
It all comes down to the fact that because we've simplified the wave propagation by assuming plane waves, we can now express the scattering matrix in this really compact form. It's a lot easier to work with computationally.
So by making this far-field assumption, we not only simplify the calculations for individual elements, but also simplify the way we describe the entire system's behavior.
Exactly. And that's a big deal in terms of computational efficiency. It allows us to model the entire RIS system without getting bogged down in all those nitty-gritty details of near-field interactions.
So we're gaining a lot of speed without sacrificing too much accuracy. That's the sweet spot we're looking for, right?
Precisely. And the research actually goes a step further to prove that this trade-off is worth it. They compare their far-field approximation method with those full-blown computationally heavy simulations. And guess what? The results are incredibly close.
Let's hear it. What kind of results did they get?
They used this method to design a small RIS, just 7 rows by 2 columns. Not huge, but enough to get some meaningful data. This RIS was operating at a frequency of 3.55 gigahertz, which is in the range commonly used for wireless communication. They then calculated the ideal capacitance values for each element on that RIS, first using their new method and then with those traditional full-wave simulations.
Drum roll, please. How did the two approaches compare?
The results, which you can see in figure 2 of the paper, are really impressive. The capacitance values they get from both methods are virtually identical. That suggests that this far-field approximation is doing a fantastic job of capturing the key physics of how the RIS works.
Okay, that's really encouraging.
Yeah.
It seems like this simplification isn't just a mathematical sleight of hand. It's actually grounded in the real-world behavior of electromagnetic waves.
Right, and that's what makes it so promising for real-world applications. In many cases, the distances involved naturally put us in the far-field region, so this approximation isn't just a theoretical trick, it's actually reflecting how these systems operate in practice.
So we've got the theory, we got the simulations, and everything seems to be lining up. But I have a feeling this research didn't stop there, did it? They went a step further and actually built a physical RIS, right?
You know it. They put their money where their math was. They fabricated a small-scale RIS and put it to the test in a real-world experiment. But we'll save those juicy details for the next part of our deep dive.
Sounds good. I'm on the edge of my seat.
It's going to be good.
All right, so back to the deep dive. We left off talking about the impressive results the researchers got from their far-field approximation method. Really promising stuff.
Yeah.
But you mentioned they didn't stop at simulations.
Oh, definitely not. They took it a step further, which is what I love to see. They actually built a physical RIS to see how it performs in the real world. Really put that theory to the test.
That's what separates the mathematicians from the engineers. So let's dive into that experiment. How did they go about building and testing this RIS? What were they looking to prove?
Okay, so first, they fabricated a small-scale RIS. It was the same size as the one they simulated, just 7 rows by 2 columns, operating at that same 3.55 gigahertz frequency. And get this, they incorporated varictor diodes into each of the elements.
Now, remind me, what are varictor diodes again?
They're essentially tiny electronically controlled capacitors. Think of them like little knobs that allow you to fine-tune the capacitance of each element on the RIS, giving you real-time control over its response. Super cool.
So they could dynamically adjust the behavior of the RIS, like on the fly.
Exactly. They could tweak how each element reacts to the incoming signal. This is crucial for optimizing the RIS in real-world scenarios where conditions are constantly changing.
Right, because the signals in the environment aren't static.
Right.
Smart thinking.
Yeah.
So how did they actually test this tunable RIS? What kind of experiment did they set up?
They use a technique called bistatic radar cross-section measurements, or BRCS for sure. It's a fancy way of saying they sent a signal towards the RIS and measured how much of that signal was scattered back in different directions.
So like shining a radar on it and seeing how the signal bounces off.
Yeah, pretty much. And by carefully measuring the BRCS at various angles, they could map out exactly how the RIS was redistributing the incoming signal. And remember, they had already optimized the RIS for a specific receiver location using their simulation, so they expected to see a concentrated peak in the BRCS at that precise angle.
Makes sense. If they tuned it to focus the signal towards a particular point, the measurements should back that up. Did they?
They did. The results are shown in Figure 3 of the paper, and they're pretty awesome. The experimental measurements show a clear peak in the BRCS at that intended angle, meaning the RIS is successfully focusing the signal as predicted.
Wow, that's a pretty convincing result. So we've got the theoretical model, the simulation results, and now even real-world experimental data, all pointing in the same direction.
It's a trifecta. It really highlights the potential of this far-field approximation method. It's not just a theoretical curiosity, it's a practical tool that can predict and optimize the behavior of real RIS systems. And what's really exciting is that they also compared the performance of their RIS with a simple copper reflector.
Oh, that's an interesting comparison. Why copper?
Well, copper is a great reflector of electromagnetic waves. It's a kind of baseline to see how the RIS stacks up against a more traditional reflecting surface.
Okay, so how did the RIS fare against the copper?
The RIS actually outperformed the copper reflector in terms of focusing the signal towards the receiver. Even with this small-scale prototype, the RIS showed a significant advantage over a simple passive reflector.
That's impressive. So even a relatively small RIS can have a big impact on signal strength and direction.
Right.
It really underscores the power of this technology to manipulate wireless signals in a precise and controlled way.
Absolutely. It opens up so many possibilities for improving wireless coverage, enhancing signal strength, and even reducing interference. But of course, this is just the beginning.
Right. As with any emerging technology, there are still challenges to overcome and lots of potential to unlock.
Exactly. And that's what makes this field so fascinating. There's so much more to explore and discover.
Back again for our final deep dives into the world of RIS. We've seen the theory, the simulations, even a real-world experiment, all super impressive. But now I want to look ahead. What's next for this tech? Where do we go from here?
Yeah, it's one thing to demonstrate the potential in a controlled lab environment, but translating that to large-scale, real-world deployments is a whole other challenge.
So what are the biggest hurdles we need to clear to make RIS a part of everyday life? What's holding us back?
Well, think about it. We've been talking about a relatively small RIS, just a handful of elements. But imagine scaling that up to a surface with hundreds or even thousands of those tiny antennas, each needing to be individually tuned and controlled. The complexity explodes.
Yeah, finding that perfect configuration for each antenna, especially when you have so many of them. And in a real-world environment where things are constantly changing, it's got to be mind-boggling.
Exactly. So one of the biggest challenges is developing intelligent algorithms and control mechanisms that can handle that level of complexity. It's not just about brute force computation. We need smart strategies that can adapt in real time to optimize the RIS performance as the environment changes.
It's like instead of just having a bigger hammer, we need a more sophisticated toolbox.
Right. And then there's the question of physical integration. Where do we actually put these RIS panels? On walls, ceilings, furniture? How do we seamlessly incorporate them into our surroundings without it looking like a sci-fi movie set?
Yeah, aesthetics definitely matter, especially when you're talking about something that's going to be so pervasive in our environment. It needs to blend in, be almost invisible.
Absolutely. We need to think about new materials and fabrication techniques, maybe thin, flexible films that can be applied to various surfaces, or coatings that can be integrated into existing structures.
Okay, now for the million-dollar question.
Yeah.
How much is all this going to cost?
Yeah.
Can we actually make this tech affordable enough for widespread adoption?
Cost is definitely a key factor. The economic viability of RIS will depend on finding cost-effective manufacturing processes and materials. We need to drive down the price per element without sacrificing performance.
And while we're talking about practicality, what about energy consumption? We want this tech to be efficient in every sense of the word, not just in terms of computation, but also in terms of power usage.
Absolutely. We don't want to create a new energy hog. RIS systems need to be designed with energy efficiency in mind from the ground up.
And of course, we can't forget about security and privacy. When you have a technology that's manipulating wireless signals, it raises some red flags. Could this tech be vulnerable to hacking or unauthorized access?
Security is definitely paramount. We need robust protocols and encryption methods to safeguard these systems against malicious attacks. And equally important is the privacy aspect. We need open discussions about data collection and usage, ensuring that any data handled by these systems is treated responsibly and ethically.
Transparency and trust are going to be key to getting the public on board with this technology.
Absolutely. People need to understand how it works and feel confident that their privacy is being protected.
One final thought. It seems like RIS isn't meant to replace all our existing wireless technologies, right? It's more about integrating with and enhancing them.
Exactly. Think of it as adding a layer of intelligence to our existing wireless infrastructure. RIS can work in conjunction with Wi-Fi, cellular networks, and other technologies to optimize coverage, boost signal strength, and reduce interference.
So it's about creating a more intelligent and adaptable wireless ecosystem, where RIS plays a key role in maximizing performance and overcoming limitations.
That's the big picture. It's about creating a truly seamless and reliable wireless experience.
Well, I think we've covered a lot of ground today. From the intricate math to the real-world challenges and the incredible potential of RIS, this has been a fascinating deep dive.
It has. It's a rapidly evolving field, and I'm excited to see what the future holds for this game-changing technology.
And to our listeners, if you're as intrigued by this technology as we are, don't stop here. Dive deeper into the research, explore the online resources, and maybe even contribute to the development of this revolutionary field.
You never know. The next big breakthrough in RIS could come from one of you.
On that note, we'll wrap up this episode of The Deep Dive. Thanks for joining us, and we'll catch you next time for another deep dive into the cutting edge of technology. Welcome to The Deep Dive. Ready to get our hands dirty with some seriously cool math?
Always.
Awesome.
Yeah.
Today, we're taking on Reconfigurable Intelligent Surfaces, or RIS. We've all heard the hype walls that amplify signals.
Right.
But how do we actually make that happen? That's where the optimization challenge comes in and things get, well, a little bit complicated.
Yeah.
The paper we're diving into is called Reducing Simulation Effort for RIS Optimization Using an Efficient Far-Field Approximation.
Yeah, they really get into the nitty-gritty of the equations and how they tested this stuff out.
So yeah, buckle up.
What I find really interesting about this paper is how they make the whole optimization process a lot simpler. You know how figuring out the best setup for an RIS, to get the signal as strong as possible,
Yeah.
usually needs like a ton of simulations.
Oh, yeah.
Every time you adjust the RIS elements or move the transmitter or receiver, even a tiny bit,
Yeah.
you'd have to start a whole new simulation, right?
Right.
And that takes so much computing power and time.
It's like trying to rearrange furniture in a room, but you're blindfolded. And every time you move a chair, you got to simulate the entire room's acoustics again.
Exactly.
It's nuts.
And this paper's saying they've got a shortcut.
That's what they claim, and I'm really curious to see how they actually do it.
Me too. So they're basically crunching down all that computational work without losing accuracy.
That's the idea.
Yeah.
And they definitely bring some serious math to the table to back it up.
Okay, lay it on us. What's the secret sauce?
Their trick is this really clever far-field approximation. They basically create a kind of master key, like a cheat sheet almost.
Okay.
It lets them figure out how things would work in lots of different situations without having to do separate simulations for each one.
That sounds pretty powerful.
Yeah. The heart of it all is equation 1. It's an approximation for how the transmitter and each little part of the RIS connect with each other.
So equation 1, that's where the far field magic starts.
Exactly.
All right, hit us with it. Okay, so here's the equation. LAS-TXM, DTX-UP, ATX-GM, ETX-DX-GM, lambda, EG-TXM, DTS-GX.
Whoa, okay, let's break that down a bit.
Yeah, let's unpack it. So SES-TXM, that's like the piece of the puzzle we want to figure out.
Okay, says the accept, got it. What about everything else in there?
Okay, so the first part, sexy-X mana lambda, that takes care of any issues with impedance matching in the RIS element. Basically, it tells us how much of the signal bounces back instead of being absorbed and re-emitted.
Right, so not all of the signal is going to be perfectly redirected. There's going to be some loss, right?
Exactly. And then we have sexy TSGM, gamma TXGM. This part has to do with how strong the transmitter's signal is and how well the RIS element can catch that signal depending on its direction.
Okay, makes sense. Now, what about this bit? Phrase CT, DTX man lambda, that looks kind of intense.
Oh, that's just about distance and wavelength. DTX manner is the distance between the transmitter and the RIS element. And lambda, that's the wavelength. It's basically saying that the signal gets weaker the farther it travels.
Makes sense. The farther you shout, the quieter it gets, right?
Aha, exactly.
Yeah.
Now, this last part, EJ fractly pi DTX M lambda, that might look scary, but it's just dealing with the phase shift of the signal.
Phase shift?
Yeah, like, you know how electromagnetic waves are always wiggling? The phase is like where they are in that wiggle.
Okay.
And even tiny changes in that can make a big difference in how waves interfere with each other.
Wow. So equation 1, it's not just a bunch of random symbols. It's like a recipe for understanding all the things that affect how a signal travels, right?
Exactly. It's pretty clever when you think about it.
It is.
And by using this for each part of the RIS, they can basically map out how the whole surface will interact with the signal.
Cool.
They even have a picture to help us visualize all this. Figure 1 shows the setup they're working with.
Okay, so what are we looking at here?
Well, there's a small RIS. It's just a 7x2 array, a grid of those elements. It's placed between the transmitter and the receiver.
Right.
And here's the important part. The transmitter and receiver, they can't actually see each other directly.
Interesting.
Yeah. This is to show how the RIS can make communication work even in situations where it normally wouldn't.
So the RIS is kind of like a middleman, bouncing the signal between them.
Exactly.
Okay. What else are we seeing in this figure?
You see those two angles, RA and bake?
Yeah.
Well, RA is the angle the signal from the transmitter hits the RIS at.
Okay, so the incoming angle.
And RA is the angle it bounces off at toward the receiver.
The outgoing angle. Got it. So these angles are pretty important, huh?
Oh, they're key. The angle, it affects how much of the signal each element captures. And that determines where the signal goes after it bounces off.
That's like playing pool. You got to hit the cue ball just right to make the other balls go where you want them.
That's a perfect analogy.
Right. Okay, cool. You mentioned earlier that they need the whole scattering matrix, or S matrix, to really optimize the RIS. How does this far-field approximation help with that?
Well, the S matrix, it's like a giant map of how the whole system works. The RIS, the transmitter, and the receiver all interacting with those electromagnetic waves.
Okay.
Each entry in the matrix tells you how different parts of the system are connected.
It's like a giant lookup table for how signals interact.
Yeah, you got it.
Okay.
So the cool thing about the far-field approximation is it lets them figure out the whole S matrix with just one simulation.
Really?
Yeah. First, they simulate just the RIS by itself, which gives them CRIS in equation 2.
Okay.
And then they use the far-field approximation from equation 1 to calculate the connections between the transmitter, the RIS, and the receiver.
So they use the approximation to fill in the missing pieces without having to run a whole bunch of separate simulations.
That's exactly it.
And that saves a ton of time and computing power, right?
Right. And you can see how they build the full S matrix in equation 2. 0 is approx 0, and osrec is 0, 0, 0 is SRX is beta, and SRX beta, and SRX and subox 0 is beta, and STX alpha, and STR alpha, and STRX error, and STRX error. Those are for the transmitter and receiver. But We can pretty much ignore those.
Okay, so the key here is they only need one simulation for zeros-R.
You got it. The rest is all thanks to that far-field magic.
That's incredibly clever. They've found a way to make the whole thing much more efficient without seeming to lose any accuracy. But any theory has to be tested in the real world, right? Did they actually try this out?
Oh, they definitely put it to the test. And that's where things get really exciting. They built a real prototype to see if this far-field approximation actually works in practice.
Yeah, it's not just theoretical. They really wanted to see it in action. And their setup was pretty cool. They built a small RIS prototype working at a frequency of 3.55 gigahertz.
Okay.
It was a 7x2 array of elements, all on a standard FR4 printed circuit board. So, a fairly simple design for a first test.
Yeah. Makes sense to start simple.
How did they actually test it?
They placed both the transmitter and receiver antennas 2 meters away from the RIS.
Oh.
That distance is important because it makes sure they're in the far-field range where their approximation should work best.
Right, so they're setting things up so it matches the conditions of their model.
Exactly. Careful planning. Now, for the antennas, they used horn antennas for both the transmitter and receiver.
Horn antennas.
Okay.
Why those?
Well, they have these really focused radiation patterns. They send out signals in a very controlled beam.
So that helps reduce any unwanted reflections that could mess up the measurements.
Right on. They also did something called time gating to isolate the specific signal they were looking at.
Time gating. What's that?
Imagine you're taking a picture with a flash, but in a room full of mirrors.
Okay, yeah.
You'd get a bunch of reflections and the picture would be blurry, right?
Yeah.
Time gating is like having a super fast shutter on your camera. So you only capture the first flash and block out all those reflections.
I get it. They're filtering out any extra signals that could contaminate the data.
Exactly. They're really trying to make these measurements super precise.
Cool. What about the optimization itself? What were they actually trying to optimize?
Well, they focused on one specific scenario. The receiver was right in front of the RIS at an angle of unbelated degrees, and the transmitter was off at an angle of unde equals 30 degrees.
Okay. And what were they trying to achieve in this scenario?
They wanted to find the best capacitance values for each element in the RIS to make the signal at the receiver as strong as possible.
Okay, and why is capacitance so important here? Remind me.
Well, each element in the RIS, it's basically a tiny little antenna. By changing the capacitance, you change the resonant frequency of each element.
Right, and that determines how it interacts with the electromagnetic waves, right?
Exactly, like tuning a radio to pick up a specific station. By carefully choosing the capacitance values, they can control how the RIS reflects the signal and focus it right at the receiver.
And this is where the far-field approximation comes in handy, right?
Yeah.
They can use it to predict those optimal capacitance values without needing to run tons of simulations.
Exactly. They used their approximation method to calculate those values, and then they compared them to the results from a full-blown, computationally expensive simulation. And guess what?
All right.
The results, shown in figures 2b and 2c, were super close.
Wow, so their shortcut actually worked? That's pretty amazing.
Yeah, it really did. Their method not only made things easier, but also seems to be really accurate. But of course, they didn't just stop at theory, they took it a step further and built a prototype.
They actually built it. Awesome.
Yeah. They used these things called varictor diodes to implement the capacitance values they calculated.
Varictor diodes, what are those?
It's a special type of diode, and its capacitance can be controlled by changing the voltage across it.
Oh, like an electronically tunable capacitor.
You got it.
So by changing the voltage, they could adjust the capacitance of each element to match what their approximation method predicted.
Exactly, like having little tiny knobs on each element to fine-tune the whole thing.
So cool. But how do they measure the performance of the prototype? How do they know if it was actually doing what they expected?
Okay, so for that, they measured something called the bastatic radar cross-section, or BRCS.
A static radar cross-section, okay.
You can think of it like this. You shine a flashlight on a mirror in a dark room. The BRCS is basically how much light bounces back from that mirror towards you.
Ah, okay. So in this case, they're measuring how well the RIS is reflecting the signal from the transmitter to the receiver.
Exactly. It tells them how effectively the RIS is focusing the signal, so they can compare their theoretical predictions to the actual performance of their prototype.
Got it. So what did they find? Did the prototype live up to the hype?
The results were pretty impressive. In Figure 3c, you can see the BRCS measurements they got, along with the predictions from their far-field approximation and the full simulation. And get this, All three are really close.
That's fantastic. So their approximation wasn't just a theory, it actually predicted how a real RIS prototype would behave.
Yeah, it was a real win for their approach. But there's one more interesting detail here. The BRCS for the RIS goes above plus 15 dB at an angle of I-phi equals 0 degrees.
That's 15 dB. Okay, what's so special about that?
Well, to put it in perspective, they also did measurements with just a plain couple reflector, the same size as the RIS, something that just bounces the signal back without any fancy manipulation.
Right.
Even that basic reflector did okay, but the RIS was way better, especially at RIS 0 degrees.
So even this small prototype RIS with just a few elements showed a clear advantage over a passive reflector.
Yeah, it's a really exciting demonstration of what RIS can do.
That's awesome. So their method works, they built a prototype, they measured it, and it all seems to check out. But no research is perfect.
Right.
Were there any limitations that they mentioned?
Oh, of course. There's always more to explore. They pointed out that their far-field approximation, as you might guess from the name, it might not be as accurate when the transmitter and receiver are super close to the RIS.
Because the far field assumption doesn't hold up as well when things are close together.
Exactly. When things get too close, those near-field effects start to become important, and the approximation might not work as well.
Right, like using a road map to navigate your living room, it's not really designed for that level of detail.
Yeah, good analogy.
So this means their method might not be the best for things like indoor Wi-Fi, where devices are often really close to each other.
Yeah, that's a good point. For those scenarios, you'd probably need more complex models that take those near-field effects into account.
Makes sense. What else did they mention?
They also talked about exploring more complicated shapes for RIS. Their prototype was just a simple, flat rectangle. But to really push the boundaries, they're looking at things like curved surfaces or even 3D structures.
Oh, wow. Like going from building with flat Legos to using all sorts of curved and angled pieces.
Exactly. Those more complex shapes could give them a lot more control over how they manipulate electromagnetic waves, which could lead to even more amazing applications.
It's really fascinating to think about.
Oh, definitely. And beyond the shape, there's also a lot of potential in exploring different materials and ways to actually build these things.
Yeah, like how the materials and construction methods affect how efficient and effective the RIS is.
You got it. So this paper is a great starting point, but it's really just the beginning of the journey for RIS optimization.
We've covered so much in this deep dive, from all the math and equations to how they actually tested this out in the real world. It's really mind-blowing to see how the simple idea of using intelligent surfaces to control signals can lead to such complex and powerful applications. Wow, we've really gone deep into the weeds with this paper. It's amazing to see how this seemingly simple idea, intelligent surfaces that can manipulate signals, it turns out to be this whole world of complicated math, clever experiments, and all these potential applications.
It is. It really shows how creative these researchers are, constantly pushing the limits of what we can do with wireless communication.
Absolutely. And as we've been talking about this research, it's a huge step forward, but it also opens up so many more questions and avenues to explore.
Yeah, definitely.
What are you most excited about, thinking about the future of this technology?
Honestly, I think about access.
Access.
Like to high quality internet. Imagine a world where it doesn't matter where you live or how much money you have, everyone has a great internet connection.
Oh, wow, yeah.
RIS could be a game changer for bridging that digital divide, making sure everyone can tap into all the resources and opportunities online.
That's a really powerful thought.
Yeah.
It reminds us that technology isn't just about the cool gadgets and the science. It's about people.
Exactly. And RIS could really empower individuals and communities, especially in places that have been left behind.
Totally. Think about the impact on education, healthcare, even economic development in areas that haven't had access to reliable internet.
Yeah, it could change everything.
It's exciting to think about.
Yeah.
But of course, like with any new technology, there are challenges, things we need to think about carefully. What are some areas that researchers and policymakers should be focusing on as RIS becomes more widespread?
Standardization for sure. As more companies start building and deploying RIS systems, we need to make sure they can all work together, talk to each other.
Right, so we don't end up with a bunch of different systems that can't communicate with each other, like a bunch of puzzle pieces that don't fit.
Exactly. Standardization is key to making sure this technology can really take off and benefit everyone.
Makes sense. Another thing that comes to mind, especially as we rely more and more on wireless networks, is security. How can we make sure these RIS systems are safe and protected?
That's a really important point. I mean, the more we depend on these networks, the more important it is to protect them. Luckily, researchers are already working on ways to make RIS systems more secure.
Oh, really? How?
One way is to actually build security features right into the RIS elements themselves, like at the hardware level.
Wow. So not just relying on software, which can be vulnerable to hackers.
Right. Building security right into the hardware could make these systems way more resistant to attacks.
That's really interesting. It sounds like there's a lot of promising work being done to address those challenges. As we wrap up this deep dive, I have one last question for you and for our listeners to think about. We've talked about how RIS can change our homes, our cities, even our individual lives. But what about the bigger picture? How do you think RIS will change society as a whole, the way we connect with each other, the way we interact with the world around us?
That's a great question and a really important one. Like any powerful tool, RIS has the potential to do amazing things, but also, maybe some not so great things.
Yeah,
We have to be really thoughtful about how we use it, make sure it benefits everyone and doesn't create new problems.
absolutely. It's on all of us to shape the future of this technology and make sure it's a future we want to live in.
I totally agree. We have the power to steer this technology in the right direction.
Well said. Thank you so much for joining us on this deep dive into the world of reconfigurable intelligent surfaces. It's been a fascinating journey. We hope you learned something new and that you'll keep exploring, keep asking questions, and keep diving deeper into the things that spark your curiosity. That's what the deep dive is all about. Until next time.